Hello everyone and welcome back to FatalSec. In this video, we are going to discuss some of the basic arithmetic operations that exist in ARMv8 assembly. In addition to discussing these, we are also going to discuss a few different modifications to these instructions that tend to be present in a lot of instructions in ARMv8 assembly. And they also do very interesting things like setting the CPSR or SPSR register after the instruction is executed. So, the reason why we are going to discuss these basic arithmetic instructions first is because arithmetic is easy. Everyone sort of knows about adding, subtracting, or multiplying, right? So it's very easy for me as well to start explaining with these operations first, and once we get a basic understanding of these instructions, then we will take on to some of the more complex and interesting arithmetic instructions. Alright, so to start off with the very basics, we can simply add, subtract, or multiply numbers in ARMv8 architecture using a set of instructions. So let's start with a simple addition program. If you look over here, to add two numbers, we have this add instruction. This add instruction takes three operands. For instance, here in this example, it's using W2, W1, and W0 as the operands, and how it will work is pretty simple. The first operand is going to be our destination where the final result will be stored. Then the next two operands are going to be our source. So firstly, the processor will look into the W0 register, which contains hex 7, and then it will look into W1 register, which contains hex 4. Then it will perform the addition operation. So the addition of 7 and 4 is going to be 11, right? Now this result will then be stored back to the register pointed out by the first operand, which is W2. Okay, then this W2 register can be used directly by other instructions to access the result of the addition operation. Let's now create a simple addition program in ARMv8 assembly, and for that I am going to create a new file called addition.s. Then we first need to declare a global symbol using .global declarative. Let's name the global symbol as _start. This start will act as an entry point for the program from where it starts executing. And this is what we learned in the very first lesson of this series, right? Then we are going to declare .text section using .section.text. And this section is basically going to contain all our assembly instructions. So inside this section, we can define our start label. Now inside this start label, firstly, we are going to use move instructions to store 7 and 4 in the respective registers. So to move, let's say 7 in W0 register, we can write move W0, #7. Now, if you went through the previous video where we have explained different addressing modes, you must be aware now that this instruction is immediate addressing mode, where we are storing the immediate constant value 7 into the register W0. Similarly, let's store 4 in W1 register like this. Okay, and then to perform the addition operation, we can use add instruction. And let's say we want to store the result in W2 register. So this is going to be our first operand, followed by the other two operands, which are W0, W1, right? And then to terminate or exit the program normally, we can simply paste this code, which we have discussed in the first lesson of this series, where we are using a system call to call the exit function by setting this 54 as a exit code, right? So this is it. We can now save this assembly code. So over here we now have our addition.s program. Let's assemble it and build the executable. So for that we have a ARC64 Linux GNU assembler. This will take this addition as a input and it will generate addition.object file as an output. There we go. Now this is not the final executable. So to build the final executable, we are going to use another tool called linker, which takes this addition.object file as an input and it will generate the final executable with the name addition for us. So now we have our final executable. Let's try to run it. Obviously we have not printed anything on the console, so it will simply terminate by setting the exit code which we have set in the program, which was 54, right? Let's execute, and to look at the exit code we can use echo $? There you go, 54 is the exit code. So if the exit code is 54, we can assume that the program executed normally. Okay, let's now try to see what's going to happen with the registers during the execution, and for that we are going to use GDB debugger. So if you don't have the GDB debugger installed already, please install it first, and then you can simply load the program in your debugger using GDB followed by the executable, which is addition. So now it says reading symbol from addition, no debugging symbol found, which means the executable is loaded by the debugger. And to see the disassembly of this executable, we can use disassemble command followed by the global symbol which we set, which is _start. So this is the disassembly, and this is exactly what we have coded in our program. So you can see that the first instruction of our program is loaded at this memory location, right? So let's set a breakpoint to this location using break followed by the address, enter, and now it says breakpoint 1 is set at this address. Now let's start execution by typing start command, enter, and now you can see that the execution is stopped at the very first instruction where we set our breakpoint, right? And if we scroll up a bit, we can see all of the general purpose registers are initialized with 0, right? Let's now step into the program and execute this first instruction using step I command. So now you see the first instruction is executed, and now the debugger is waiting at the next instruction. Now according to the first instruction, which should have set 7 into W0 register, right? So let's have a look at the register again, and there you go, in the X0 register we have 7, right? Similarly, let's execute the next instruction. So now the next instruction is executed, and our program counter is now pointing to the next instruction to be executed. And according to the previous instruction, 4 should be stored into W1 register, right? So let's have a look at the W1 register or X1 register, and it's set to 4. Perfect. Then let's execute the next instruction, which is the add instruction, and this is responsible for performing the addition. Let's see. So now the addition instruction is executed, and what we understood so far is that the result is going to be stored into W2 register, right? So in W0 we have 7, in W1 we have 4, and if we perform the addition of 7 and 4, it's going to be 11, right? So that 11 value should be stored into W2 register after execution of this instruction. So if we look at the X2 register, it says the value is hex B, which is nothing but 11 in decimal. So that's how the addition instruction works. We can simply quit the program now using Q command. Let's now see a special case of addition. For that, let's open up the program again and modify the values. So the name of our file is addition.s. Now let's assume that instead of this 7, I am going to store a very long integer value. Because we are using the 32-bit version of the register, the maximum value which a 32-bit register can store is basically all ones, right? Which is nothing but hex 8 times f. Okay, so this is the maximum value which a 32-bit register can handle. Let's leave the rest of the code as it is. Save this. Now because we have changed the code, we need to assemble the program again using ARC64 Linux GNU assembler, and then to generate the final executable we are going to use the linker. There we go. So now we have the modified version of the addition program. Let's directly open it up in the debugger using GDB addition, disassemble the program. So now here we can see that the first instruction is move W0 comma hash hex FFFFFF f, which is 8 times f. Let's set the breakpoint at the very first instruction, just like what we did earlier, and start the program. So now the program counter is set to this instruction, and after executing it, this value is stored into W0 register. Let's see. Yes, our X0 register is now containing 8 times f. Similarly, let's step over to the next instruction. So now W1 register should be having 4, right? Now here comes the interesting part. Let's execute the addition instruction and see what do we get in the W2 register. Ideally we should get 8 times f plus 4. So if I open up the calculator app and perform the addition manually, 8 times f plus 4, we get this very long hexadecimal value, right? So let's see it in the debugger. After stepping over the addition instruction, in X2 register we have only 3. Why? It should be this value, right? So to understand what happened here, we have to go back to the basics. Over here, assume that we have a 32-bit register, right? This means that the register can only store 32 bits at a time, and we are storing 8 times f, which is nothing but all ones in the register. So our 32-bit register looks something like this now. Then we have to add 4, which is 0100 in binary, right? Let's represent this as well in 32-bit register. Let's perform the addition in binary itself. So here we have 1 plus 0, which is 1. Then in the next bit we have 1 plus 0, which is again 1. Okay, now let's come to the next bit where we have to add 1 with 1, and this results in 0 with the carry, right? Now this carry will be added to the next bit. So here we now have 1 plus 1, which is again 0 with the carry bit. Then this carry bit will be added to the next bit, which is 1. So now again we have 1 plus 1, which will result in 0 with another carry bit, and this will go on like this till the last 31st bit. Okay, now here we have this carry bit 1, which will be added to 1 again, and the result is 0 with the carry bit, which should be stored in the 32nd bit of the register. But since our register can only store 32 bits at a time, this extra bit will be discarded and the result will become -3. Here in this example, the extra carry bit was discarded, and if we look at the CPSR register, the carry flag is not yet set. But ideally this should be set because the carry is generated, right? And that's because we have used a simple addition instruction to perform the addition. What this instruction does is it ignores the flags during an arithmetic operation. But sometimes there are situations when we want to track this carry bit to check whether the result of the operation resulted in a carry bit or not. So for such cases, we have a modified version of add instruction, which is called add s. Let's quit the debugger for now, open up the addition program again and modify this add instruction and simply put add s. So this s basically stands for set flag. This will tell the processor to set the flags as per the result of the arithmetic operation. Let's save the program and assemble it again. Link, and now we have again a modified version of addition executable. Let's quickly open it up again in the debugger. Disassemble the start symbol, set the breakpoint at the very first instruction and start execution. Let's step over the first two instructions quickly, and now our program counter is at add s instruction. Let's step over it and see what do we get in the result. So if we have a look at our X2 register, which is holding the result of the addition, it's still 3, which is okay. But if you see at the CPSR register, it's modified now and this carry flag is being highlighted over here. This shows that the carry bit is set as a result of the addition operation. We can also check this CPSR flag manually. So if we type in 4 registers, it will show us the values of all the registers, including the special registers. And there it shows us the CPSR register value as hex 2020 1000, right? And this C represents that the carry flag is set. But how we can examine this hex value? So to specify this carry flag, out of this value a specific bit has to be set, and to identify which bit is responsible for the carry flag, we can have a look at this ARMv8 architecture documentation. And if we scroll down a bit, we have the field descriptors, and from here we can observe that the carry flag is present at the 29th bit. So let's say you have this value of CPSR register. To figure out whether the carry flag or the carry bit is set or not, you can simply copy this value, open up the calculator application and paste it in the hexadecimal form. Okay, and right down below it will show you the binary representation of this value. And if you look at the 29th bit, which is starting from 0, here this is the 16th bit, 17th, 18th, 19th, and this is the 29th bit, right? And it's set to 1, which means the carry flag is set. Okay, let's now move on to the next arithmetic operation, which is subtraction. So the subtraction operation also works in a similar way. Consider this example. Here, to perform subtraction operation, we have sub instruction followed by the 3 operands, where the first operand is going to be the destination and the other 2 operands are going to be the source. So considering this example, here we have W2 in the first operand, where the result of the subtraction operation will be stored. Then we have W0 register, which is going to contain 7, and in W1 register we have 4. So if we subtract 4 from 7, we get 3, right? So this 3 will be then stored into W2 register in the end. To demonstrate this, we are going to create a new program. Let's say subtract.s. Firstly, as always, we need to declare the global variable using .global declarative followed by the symbol name, which is _start. Then all our code basically goes into the .text section of the binary. So we can define the text section using .section.text, and over here we can define our start label. Now, just like what we did earlier, first we are going to use the move instructions to store our 2 operands into the respective registers. So the first operand, which is 7, is going to be stored into W0 register, and then the second operand, which is 4, is going to be stored into W1 register, right? So these are our immediate addressing modes, as we have already discussed. And once we have set up our 2 operands, we can use the subtract or the sub instruction to perform the subtraction operation. And let's say we want to store the result into W2 register. So this first operand, so this W2 is going to contain the result of our subtraction followed by the 2 operands, which are W0 and W1. All right, let's now paste the exit routine to make sure that program exits normally. We can save our code at this point, and all we need to do is now to assemble this code using ARC64 Linux GNU assembler, and it's going to generate an intermediate file, which is our object file. And then using ARC Linux GNU linker, we can finally generate our executable. So now we have this subtract executable. Let's open it up again directly into the GDB debugger to see all the instructions in real time. Let's now run this executable in the GDB using GDB followed by the executable, which is subtract. And let's look at the disassembly of the global symbol, which is _start in this case. So our first instruction is present at this memory location. Let's copy it and set up a breakpoint using break command. And to start execution, we can use start, enter. So as usual, initially all the general purpose registers are initialized with 0, right? And our program counter is set at the first instruction move w0 comma 7. Let's step over this instruction, and now in the w0 register we have 7, right? Similarly, let's step over to the next move instruction, which is going to store 4 into w1 register. Let's see. Yes, x1 register is now containing 4. It's now time to execute this instruction, which is going to perform the subtraction between these two values pointed out by these two registers w0 and w1. And from the previous instructions, we now know that w0 is containing 7 and w1 is containing 4. So the subtraction of these two values is going to result in 3, right? So w2 should be having 3 after execution of this instruction. Let's see. So now the subtraction instruction is executed, and if we have a look at the x2 register, it's containing 3. Now before moving forward, there is something which we have to discuss, and that is about the order of the operands. So in this example, the first operand is the source operand. So over here in this subtract instruction, the first source operand is w0 register and the second source operand is w1 register, right? And they are containing 7 and 4 respectively. Now what will happen if we reverse this order? What I mean is that if we make w1 as the first source operand and w0 as the second source operand, then what is going to be the result of the subtraction operation? Let's quit this program and quickly modify these two operands. So the first source operand is going to be w1 and the second source operand is going to be w0. Now save the code, assemble it again, generate the executable using linker. So now we have a modified subtract executable. Let's open it up in the debugger as usual. Look at the disassembly, dash the breakpoint and start the execution. Step over to the first instruction and stepping over to the second instruction, right? So now in w1 we have 4 and in w0 we have 7. This means that it will subtract 7 from 4, not 4 from 7. There is a difference, right? And we know that subtracting 7 from 4 will result in a negative decimal value. So the result of this subtraction operation will be -3. Let's see, stepping over to this instruction, and the x2 register is containing a weird value hex FFFFFFD. If we try to convert this hexadecimal value into decimal, it's this, which doesn't make any sense. It's not -3. So what's going on here? If you remember, I told you that there is a special purpose register called CPSR which contains various flags such as 0, negative, overflow, carry, etc. And during an arithmetic operation, if the result meets any of these conditions, the processor sets the corresponding flag. For example, here during the subtraction operation, the result is negative. So the processor sets the negative flag or the specific bit in the CPSR register. But there is another catch over here. ARM processors supports arithmetic operation without setting these flags in CPSR register. So at this point, if we have a look at the CPSR register, no flags are set. Let's quickly have a look manually by printing the values of the registers using info registers. And in the CPSR register, it contains hex 21000 and none of the flags are set. Let's confirm this manually as well. So from the ARM developer documentation guide, the negative flag or bit is represented by the 31st bit of the CPSR register, right? So we have this value in the CPSR register. Let's copy it, go to the calculator application in hexadecimal form and paste this value, and down below it shows us the binary representation of this hexadecimal value. And as per ARM architecture documentation, the negative bit is present at 31st bit, right, which is this one, and it's currently set to 0, which means the negative flag is not set yet. Okay, so just like what we did with the add instruction, we have to do the same thing with the subtract instruction, which is appending S to make sure that the processor sets the necessary flags in the CPSR register. So for that, let's open up our program again and make a modification to this sub instruction and make it sub S. Okay, this S is going to tell the processor to set the necessary flags in the CPSR register. Save the code, assemble it again, generate the executable. Here we have the modified tracked executable. Let's open it up again in the debugger, disassemble the start label, attach the breakpoint, and start the execution. Let's quickly step over to the first two instructions. So now we are at this subtract instruction, and currently in the CPSR register none of the bits or flags are set. Let's step over to the subtract instruction and let's see what do we get. Now if you look at the x2 register, it still contains the weird hexadecimal value, but in the CPSR register the negative flag is now set, right? And if we look at the CPSR register value, it's also changed to this hex 8020,000, and here the negative bit is set. Let's quickly check it manually as well, copying the CPSR register value and paste it in the calculator application. And if we look at the 31st bit, it's set to 1 now, which suggests that negative flag is set, right? But it's still, what's going on with this x2 register? Why we are getting this value? So this is actually -3, and if you see all f in front of a value with the negative flag set, you can say that it's a negative value. So to make sure, so then how can we print this value exactly? For that we can examine the register value, but while examining we have to make sure to typecast it to integer form. And in order to do that, we can use this print command followed by D, which tells the debugger to print only 4 byte, which is equivalent of the size of an integer, and then we have to typecast it to integer to make sure that the result is not in the hex form but in the integer form, followed by the address or the register name. So we know that our result is actually stored in the W2 register, so we can use x2 over here, enter, and there you go, it says -3, which is actually the result of subtracting 7 from 4, right? So now we have seen different versions of addition and subtraction instruction where it allows us to set the flags based on the result of the arithmetic operation, right? But this is not it. You must be wondering, what's the need of these flags if one can perform addition, subtraction, and even handle negative values without setting these flags, right? Well, in case of conditional statements such as if statement, we need these flags to check the status of the comparison. We will get into these details when we study about conditional statements in the upcoming videos. But for now, if you want to set the flag, make sure to append S in front of your arithmetic instruction. We can now quit this program and clear out the terminal. And let's now move on to the next arithmetic operation, which is multiplication. To perform multiplication operation, ARMv8 architecture provides us with the instruction called MUL, which stands for multiplication. So just like all other previous instructions, this instruction also takes 3 operands. So the first operand represent the destination, while the next 2 operands are the source values between which the multiplication will occur. For instance, in this example, the values present in W0 and W1 register will be used to perform the multiplication, and then the result will be stored back into the destination register, which is W2 in this case. So over here, W0 register is having 7 and W1 register is having 4. And if we do multiplication of 7 and 4, the result is 28, right? So this 28 value is going to be stored into the W2 register, which is our destination register in this case. Let me quickly demonstrate this by creating a simple multiplication program in ARMv8 assembly. For that, I'm going to create a new program called multiply.s, and as usual, we are going to declare our global declarative start. Then all our instructions or the code is going to be present in the .text section of the executable. So we have to define our text section over here like this, and under this we can define our start label. So as per our example, our two source operands are W0 and W1. So let's initialize them first using move instruction. Move W0 and it's going to contain 7. Then our second operand, which is W1, and it's going to contain 4, right? Then to perform the multiplication operation in ARMv8, we have MUL instruction. So the first operand is going to be the destination register where the result will be stored. So let's say I want to store the result in W2 register, followed by the two source operands, which are W0 and W1. Now the order of the operands doesn't matter over here, because if you multiply 7 with 4 or you multiply 4 with 7, the result is going to be the same. And now let's paste our exit routine to make sure that program terminates normally. Now we can save our program, and it's time to assemble it using ARC Linux GNU assembler. It's going to generate an intermediate file called the object file, and then using Linux GNU linker, we are going to generate our final executable with the name multiply. So now we have this multiply executable, which is going to perform the multiplication between the two values. So again, to analyze these instructions in real time, we are going to use GDB debugger. GDB followed by the executable name, which is multiply. Enter. Let's look at the disassembly of our start label. There we go. So our first instruction is present at this memory location. Let's set up a breakpoint over here using break command, and now we can simply start execution of this program using start command. So now our program counter is set at this instruction. Initially all the general purpose registers are initialized with 0, and if we step over to the first instruction, it's going to set 7 into W0 register, right? Let's see. Yes, X0 register is now containing 7. Similarly, let's execute the next instruction. So according to this instruction, 4 is going to be stored into W1 register. Let's see. Yes, X1 register is containing 4. Now it's time to execute the multiplication operation, and it's going to perform multiplication between these two values, which are 7 and 4. So 7 into 4 is equal to 28, right? Let's see. If we look at the W2 register, it's containing 1C, which is 28 in decimal, right? So that's it for this lesson. And in the next video, we are going to see how to perform various logical operations such as AND, OR, XOR, and negation that are used to complete bitwise operations on register. So stay tuned for that.